Good morning, Astronomy 1020. How are we today?
Good, thank you. How are you?
I'm well. So we're going to continue learning a little bit about some of the details of Newton's laws. We're going to talk about escape velocity, momentum, and energy today. Energy is going to be the gateway drug that takes us from Newton's laws into the world of atoms and light, which of course will be a very important chapter for our development in understanding the light from stars. So I hope a few more folks are going to join us here, although I guess we've got quite a few trolls in the background today. So let me make an adjustment. I also need to make, I need to sort of have a chat with you guys. Just a moment here. Hide non-video participants. Did I send the email? Yes, of course I did. Why would I have not sent the email, Austin?
I don't know, but I didn't get it today, so I just had to go on Blackboard. I was wondering if that's why some people aren't here.
Oh.
Yeah, I had the same thing. Couldn't find the email, so I just went through Blackboard.
Well, I need to fix that. Maybe I sent it to the Astronomy 1010 students by accident. Oops. Wait, no, that's not possible because you saw it posted in the announcements, right? So the first thing I did was you know what's weird? This is why I have it to my email. Here, let me look, just a second here. Share screen. Look, so this was sent to Astronomy 1020. Did anyone get it? There's so many trolls. You got it, Stacy. You did get it? Okay. I've noticed, oh geez. I've noticed that sometimes people, like sometimes I won't get the email and I don't understand what that's all about. That's why I started posting it on Blackboard. There's been a few times where I was the one sending it. It should bounce back to me, but it doesn't. And so I don't know what that is. That's no doubt another failing of Blackboard, which leaves much to be desired, if you ask me. It's a very clunky and inelegant system. So my only working hypothesis is that it's Blackboard's fault. But I can see, you know what, I'll send it again just because it can't really hurt, I guess. So let's just send that one more time. Send it to all users. And this is not how I exactly wanted to start the recording, but so be it. Okay, so AS1020. This is lecture for LAB4 today, live Zoom. And I'll just make a note that some people, and I'd like to know if you guys get this. Stacy got it. AS1020, some people said they did not receive the email. Here it is again. So Austin and friends, Gianna, why don't you let me know if you get that? And I think hopefully a few other people besides Stacy are going to share their video with me today. Otherwise, I'm going to really strongly consider giving you guys pre-recorded lectures, and you're not going to like that a whole lot. So,
Listen, I'm not going to be on video if I'm going to be the only one called on, okay?
Well, I understand the pressure, Stacy. It's going to be you and me, and the hell with these guys. All right, fine.
Got it.
All right, yeah. Let's show some team spirit here, you know, otherwise this isn't a class. Sharing video is important so that we can have a dialogue with each other. So you got the second one, Gianna. Okay, well, whatever. So people have the email now. And if they don't want to show up to class, that's on them. Let's start by, I have another unpleasant announcement to make. Some people are confused about the due dates for assignments, okay? Some people wrote me this weekend trying to submit their work late Sunday night, which is clearly too late. I thought I had made this clear, but I'm going to make it clear again until the message sinks in. Your last safe day to turn in homework is Saturday. And that's because I grade my papers on Sunday, as I told you guys many times. And once I grade the papers, I have to close out the assignments so that people's late submissions aren't bleeding into the next week. I don't have time to grade 2 weeks worth of homework because there's just too many students this semester. So you guys need to have it in by Saturday at the latest. Now I don't grade the first thing in the morning on Sunday. I grade usually in the afternoon or something, but I'll grade whenever I feel like it on Sunday. That's my hell day. Okay. So you can't, someone wrote me an email saying, I have until Sunday at 11:59, and I don't know where they got that idea, because I definitely didn't say such a thing. Now, most of you here who are talking with me are usually present live for class and live for the lab. So ironically, I'm telling you guys, but I'm not really talking to you. I'm talking to all them trolls in the background, and I'm talking to all those people who are watching the video later. You got to get your work in by Saturday, which I think is enough time, since you just have to kind of follow along with me. Tuesday gives you several days. Thursday is a little tough, and I have to admit, to the night students, I've been getting screwed up on the Thursday classes because the video takes so long to render that I start doing other stuff, and then sometimes there's another hour until I upload it to YouTube, and sometimes several hours until I post it. Okay, Cameron, I appreciate that support. But so I feel a little bad for the night students. I think last Thursday was particularly egregious because it didn't get up onto YouTube until, maybe 7 or 8 p.m. And I think I had posted the link, but I hadn't posted the actual video until very late at night. So that's a little tough on the night students. But even if you still have Friday and Saturday to just, watch that video and get it done. So it's a little tough on the night students on Thursday, but I'm going to work on that. But in any case, I need to grade papers and close things out. Arunsak, I can see you. Yes, thank you.
Okay, cool.
Okay, all right. So look, I said my thing that needed to be said. Hey, Devin. Okay, so with that in mind, just, let's try to get our work in by Saturday night, okay? Last class, we learned about Newton's versions of Kepler's third laws. And that's what we're going to start off again today, okay? So let's remind ourselves some issues about Newton's versions of Kepler's laws. Of all Newton's versions of Kepler's laws, the most important formula is the one that we learned at the end of last class and the one that we used several times in our homework. It's the formula that I dubbed NK3, Newton's version of Kepler's third law. And it looks a little something like this. P squared is equal to 4 pi squared a cubed over g times the sum of two masses. And this formula is going to be the basis of our lab today. The lab today is actually going to be quite similar to one of the homework problems that we did on Thursday, but we're going to do it slowly and carefully because this formula is extremely important in this class. We sort of need it to do a whole bunch of different things. Let's see what you guys remember. What does this formula do? What's the situation it describes? And what are the units we use for the variables? Just tell me anything you can about this important formula so I know where you're starting off from.
It's like finding the period between two planets or just like bodies of mass.
Yeah, it could be 2 stars, 2 planets, 2 asteroids, whatever. It could be a planet and a moon. And the masses are called M1 and M2, right? Or the masses are M1 and M2. They're separated by a center-to-center distance called A, and P is the orbital period.
I know that you
Sometimes-
have the MKS system.
And that's right. That's another key idea. So Austin, tell me about MKS units.
Well, P would be seconds.
Yeah.
A would be meters.
Uh-huh.
And then N would be in kilograms. No, wait.
I'm sorry?
Oh, no.
Are you talking to your dog or something?
No, I was just hesitating.
Oh, I see. M would be in kilograms, I think is what you said, right? You said everything correctly.
All correct.
All correct. That's how we like it. Okay, so these are the MKS units. It's important to remember, this is some practical stuff that you guys care about, because when you solve a problem, you have to know to convert to seconds, to convert to meters. And usually you get the masses in kilograms, so that's okay. Okay, now, because you learned this formula at the end of lecture, you have not quite begun to understand, or a little bit through homework, but there's a point, there's a reason why we would teach this formula in an Astronomy 101 class, because it is an essential tool in the toolkits of astronomers to analyze the properties of stars and planets and all kinds of different bodies. Let's really break down this formula into two different parts. These parts here, these parts are constants. 4, pi, and big G are numbers that do not change no matter what the situation is. So in some ways, these numbers, well, they're not very interesting right now at the first moment, right? If I wanted to bust out one of my proportionality arguments, which I've been trying to teach you about, if I call M1 plus M2 the total mass of the system, so although I could write M1 plus M2, I could also just imagine adding them together and calling that new mass the total mass. It's a new variable. I could even write this formula in the following way. P squared is proportional to A cubed over the total mass. This is a slightly cleaner version of the formula, which is using a proportionality argument to kind of ignore the constants, the numbers that don't change. And what's important here is the P, the A, and the M, those are the variables which change from situation to situation. In one of our homework problems, we dealt with Pluto and Charon, or this could be Earth and the Moon. In today's lab, it will be Earth and the International Space Station. So now I'm going to ask you guys a sort of adult astronomy question to see what you can do here. Well, actually, no. Let me start by telling you a story, an anecdote of why this formula is so important. You guys will remember, and I'm going to do something here. I'm going to share my screen with you guys, and I want to call up, I forgot to get my slides queued up here, but I'd like to call up a slide from my other course. You guys don't really get a big lecture on the history of astronomy, but I want to call that up for just a moment here. I'm going to need this. Oh dear. Okay. Let's start here. You guys will remember there was a famous Italian physicist named Galileo Galilei. And the reason why you learned a little bit about Galileo was because you learned about the local acceleration of Earth's gravity, which he discovered. Do you guys remember how Galileo discovered the local acceleration of Earth's gravity?
An apple.
No. You're thinking of the Newton story where he watched an apple fall from a tree. There's some chatters here. What's the chat people say? Cameron says a home-built ramp. That's right. Remember, Galileo had the inclined plane where he rolled spheres of different densities down it to prove that all objects fall to Earth with the same acceleration. Galileo, of course, was also famous for being the first astronomer to build a telescope for astronomical use. And he made a number of observations with this telescope, and there's one in particular I want to talk to you about. He observed Jupiter through his telescope, and he found that he could resolve Jupiter into a small disk with 1, 2, 3, 4 moons. And this is something that I do all the time at the Jacobi Observatory. When people come to visit the telescope, we'll often show them Jupiter. And in fact, one of my students, let's see if I can find it. One of my students took a lovely picture of Jupiter through our telescope. So this is the actual, I don't know, what do you open this with? Okay, so this is exactly what Jupiter looks like through our telescope. I just want to see if I can increase the size of this. You can resolve the disk of Jupiter, and you can see the little stripes from the ammonia cloud tops. And then you see 1, 2, 3, 4 small points of light that are the Galilean moons. They're named after Galileo, who discovered them. If there are any space fans out there, you may even know their names: Io, Europa, Ganymede, and Callisto. You have to take my 1010 class to learn more about these moons. In any case, Galileo was the first person to observe Jupiter through his telescope, and he discovered that there were moons revolving around Jupiter. And this was kind of a holy cow moment, because to Galileo, this meant that it was possible for objects to orbit around another body that was not Earth. Up until that point, people were unsure about Copernicus's placing of the sun at the center of the solar system. And they felt like all objects might revolve around Earth because humans were somehow the most important thing in the universe. And Galileo didn't just observe them once, but as you can see in my slideshow here, this is a page from Galileo's notebook. He observed the moons revolving around Jupiter night after night, shifting their positions. And this was kind of a holy cow kind of moment, because he was directly watching this little moon slide back and forth in front of the planet night after night after night. Galileo lived at the same time as Johannes Kepler, and so him and Kepler were contemporaries. And when he discovered these moons revolving around Jupiter, he wrote to his colleague in Germany, Johannes Kepler, who had developed his 3 laws of planetary motion. He said, "Kepler, I built a telescope and I looked at Jupiter for the first time, and you wouldn't believe this. I can see moons going around Jupiter. Isn't that amazing?" And Kepler thought about it, and he wrote back and he said, "Bro, you got to try my p squared equals a cubed on the moons. You got to tell me if the square of the period is equal to the cube of the semi-major axis, because that would mean that I'm like totally cool, and my law doesn't just work for planets, but it works for moons too." So Galileo measures the period and he measures the semi-major axis, and guess what he discovered? It didn't work. And Galileo lost respect for Kepler after that. He threw shade his way and said, "This guy thinks he knows the laws of planetary motion. He can't even describe these moons. This guy's a whack job." So he actually, now, does anyone out there, now that you've heard the story, know why Kepler's law did not work for the moons of Jupiter? Is that obvious to you guys? Space beef. It was a space beef, Austin. Yes. Why didn't Kepler's law, p squared equals a cubed, work? Why didn't this formula work for the moons of Jupiter?
Because
Oh,
the gravity was different?
yeah. Yeah, because, yes, essentially, because the
You're
flush your hands around.
reluctant to accept that answer.
So what gravity is different? What? Oh, I don't know what you mean by that. Do you mean like the force of gravity changed? Or?
Yeah, because the masses are different, and then the gravity is different as well.
That's right. See, neither Kepler nor Galileo had Newton's concept of gravity in their toolkit. They didn't even know that there was a force of gravity or that had anything to do with it. And Kepler had cooked the books by inventing an astronomical unit and years. He had sort of found that this formula would work as long as you use years in AU, because that's equivalent for when you have the mass of the sun. He basically took this out of the equation by defining Earth-Sun distances in Earth-Sun periods. And that meant that this law would not work because the mass was different. It was the masses of the things were different, and they didn't know about this formula. Suppose I had another point there, but I think I lost it. The point I was trying to make is, what if you were Galileo, and what if you were the person who had to go out to your telescope night after night after night, and you had to make observations of those moons? Now, here's the real point that I'm building up towards. If you were the person who had to go out night after night, and you had to look through your telescope eyepiece, and you could see the planet, and you watched the moon going back and forth night after night in front, back and forth in front of the planet. Which of these variables do you suppose would be the easiest to measure? The period, the distance between the moon and the planet, or the masses of the two objects? Which do you think would be the easiest to measure?
The period?
Exactly. And how would you go about, wait, who said that?
Me.
Who's me? Oh, Christopher, there you are, sorry. Christopher, yes. Yes, Christopher, the period. Can you tell me how you would do it? What would you do?
I would observe them and like measure them throughout the year.
Yeah, well, so for instance, Io, the closest moon, it has a period of 42 hours. So you don't, oh, Christopher, you're not wrong. I was just hoping for even more detail. You know what I would do, Christopher? You know what's typically done is you wait until the moon gets to its farthest extent. We sometimes call that greatest elongation. Sometimes that can be difficult to determine, but you'd wait until the moon got as far away as possible from the planet, and then you would start your stopwatch, right? And you'd let it go, and the moon would drift ... and a day later it would come back to greatest elongation, and then you'd stop your stopwatch, right? That's how we would do it. But Christopher has the correct answer. One would measure the period because, now I'm going to use some very adult language with you guys here, so I want you to prepare yourself. Astronomers refer to the period as the observable, okay? This here is called the observable. Students, if the period is the observable, why would we write the formula in this way where we solve for something that you could directly measure? The reason why we introduced the formula this way is because that's how Kepler introduced it, and we're building off of what he did. But this isn't the reason for the formula's existence. This isn't the usefulness of the formula's existence.
I would say it's because since you can observe P, you can kind of use it as like a starting point to figure out the other variable.
Right. Now, Christopher, I want to keep going with this game here. What do you think is the second easiest to measure? If you had to choose between these two.
I would say the distance.
That's correct. Now, do you have an idea of how you might go about it? Here,
Kind of.
well, so
like-
here, okay.
Like if I was looking at it through a telescope, I would kind of just see how far away it got relative to everything else.
That's sort of how Galileo did it, but here's something you probably haven't thought about yet, Christopher. When you look through a telescope and you see this little, we call this the field of view. The little scene that you see inside of the telescope is called the field of view. Your field of view is an angle. And I know it's an angle because when I take the Jacobi 16-inch telescope and I point it at the moon perfectly fills the field of view. So I know that for the telescope at the Margaret Jacobi Observatory at CCRI, the opening of my field of view has an angular size of 0.5 degrees or 30 minutes of arc, right? Or 1800 arc seconds, whatever you like. So if you did measure the distance, let's put it in quotes, the distance, Christopher, and you tried to measure it here like this, what you would actually be measuring is an angle. You would be measuring that Jupiter could get, let's say, 5 or 6 arc minutes. Sorry, you'd measure that the moon Io could get 5 or 6 arc minutes from Jupiter. So once you had the angle, how would you turn that into a distance in meters? You know, this is something I did not expect you to get, but you actually have the tools in your toolkit to do that, believe it or not.
Didn't we have like a formula from a few weeks ago to do that?
Yeah. What you would do is you'd argue that you were the observer, right? And that there was Jupiter over here and Io there. And you would now know that its greatest extent was maybe whatever I said, maybe 6, 7 arc minutes, right? And you'd have to know the distance to Jupiter, ironically, through p squared equals a cubed. You would know that Jupiter is 5 AU away. What formula would you use then to find this distance here, the A? Don't we have a formula that kind of does this for us? Think of this as a pop quiz, a warm-up before your exam, where you're actually going, you're going to have to do this on the exam. That's why I'm talking to you about this. What formula would I use in this scenario here? No one? Yes, Blair, we will have a review.
Think
I'll
the
try to. What would it-
small angle formula.
Yes, Christopher. Christopher, you're on fire today. What we would do is we would use the small angle formula, right? 2 pi over 360. But in this case, the A would actually be S, the separation between the moon and the planet. You would know the distance to Jupiter and the moon, and then you would know the angular separation. So you'd have this and you'd have this, and you would calculate S, but then S would be A in the next formula, right? What would be S in the small angle formula would become A. Does that make any sense? See, here I required you to take 2 formulas, and we're hopping across a river together, and you have to step on the stones and not fall into the drink here, okay? So that might be challenging for some of you. In any case, I wanted to show you, Christopher, wherever you are. Oh yeah, there you are. Christopher, I wanted to show you that you could do it, but it would take a couple of extra steps, right? Not quite as easy as the period. But you guys know everything you need to know to do that. So I guess that means this is the second easiest, right? This is doable. But what about the mass? You want to know what I think? I think the mass, and this is generally true in astronomy, masses are the hardest things to measure for astronomical objects like stars and planets. What are you going to do? You're going to tiptoe out to Jupiter with your Stop and Shop scale and give the thing a little dunk? How are you going to do that? How are you going to figure out the mass of a planet? Sometimes these masses are immense as well. It's not like you can put them on your bathroom scale. But there is a way to measure the masses of planets. And guess what it's called? Guess what that method is called? It's called, a little dunk, it's called Newton's version of Kepler's third law. Today, students, I introduce to you the real reason for NK3's existence. It's not to solve for the periods of planets and moons. You just watch them through a telescope. Who would want to do math when they could just play with telescopes? That's way more fun. NK3 solved for mass is the real reason that you have learned Newton's version of Kepler's third law. Sometimes astronomers refer to it as the cosmic balance beam, because it is with this formula that we measure the masses of stars and planets. And it looks like this. The total mass of the system, which is also the same as M1 plus M2, is equal to 4 times pi squared times a cubed over g times the period squared. And you guys have already used this formula in your homework for this purpose. But you probably were so busy just trying to punch the damn thing into your calculator, you were so busy doing that that you got lost in the sauce. You know, you didn't realize what the importance of it was. We'll practice this formula again during our lab today, okay? we will be using this on the test many times. So probably some practice before that would be good. Someone asked if there will be a review before the test. I would like to do that. I may have built in, I think we have a holiday or something. I may have built in a time where one of our homework sessions, instead of doing homework, we'll actually do practice problems for the test. And I think that would greatly benefit everyone in this class. Austin likes that idea. Sounds like a few others like that as well. Okay, so I'll try to make time to do that with you guys, okay? All right, I don't know, we could try a problem on this, or we're gonna use this in our labs today, so let's leave it there. Let's talk a little bit about the second Newton's version of Kepler's third law. Today I want to get around to talking about something I didn't have time for last time, and that's concepts like momentum and angular momentum. It turns out that Kepler's second law and Newton's version of Kepler's second law are the same thing. What is the second law of planetary motion that Kepler gave to us? Students, think of that as a review there, a review question. Sorry, guys, I dropped a particle and it rolled around the floor there. Oh, there it is. Okay.
Is it the law of equal areas?
Yes. And how does the law of areas go?
Equal areas and equal time?
Yeah. In other words, if you track the motion of a planet around the sun, the planet will sweep out equal units of area in equal intervals of time. So it travels a greater distance near perihelion and a shorter distance near aphelion. When Newton analyzed this law, he discovered that it was true. So sometimes people just, say equal areas and equal times. That's the short version of it. And Newton discovered that there was a cause, and the cause was something called the conservation of angular momentum. I don't want to spend a ton of time on angular momentum, but I do want to have like a quick 5-minute module on it, because it's a concept that I may want to invoke again in the future as I describe how solar systems form, as I describe how galaxies form. For me to explain angular momentum to you, we're first going to have a pre-discussion about regular old linear momentum. So let's do a quick module on this. Let's start off with a concept called linear momentum, which you may have learned about in a high school physics class if you ever took something like that. Does anyone out there know what momentum is? I know some of you have had science courses in high school, or maybe you've taken another physics class here at community college.
Would it be like the force of something as it's in motion?
That's what it feels like, but it's not a force. It has different close units.
The velocity in the direction?
Pardon, Austin?
Is it velocity in a direction?
Kind of. So for some reason in physics, the variable they use for momentum is the letter P. I'm not exactly sure why, but historically we use P for momentum. I think they've used M for too many things already. And the definition of momentum is the product of a moving object's mass times its velocity. And similar to what you were saying, Austin, sometimes I like to think of it as the amount of oomph of a moving object, if that makes any sense. It's the amount of oomph of a moving object, right? So momentum is something that we sometimes intuitively understand. What's important about momentum in a physics sense, the reason why physicists love concepts like momentum is they are a little more abstract to think about than velocities. They're a little more abstract to think about than masses. But what makes them so valuable to scientists is that momentum is something called a conserved quantity. That's kind of a buzzword, so we're going to write it down. It's a conserved quantity. And you're going to see a couple of these today. The conserved quantity statement means that the total momentum in a box, the total momentum in a closed system is constant. And when the total momentum in a system is constant, it gives you Nostradamus-like powers to predict the future of what will happen when things collide or smash into each other, right? So, you know, I did have a little demo on this, but I foolishly left it in my office. So what I'm going to do is I'm going to borrow the concept from YouTube here, or I'm going to borrow the demo from YouTube. Have you guys ever seen the doodah called Newton's Cradle? You've probably seen this before. It's a little Spencer's gift office toy that you give to board executives, okay? So I could do without the lame guitar soundtrack though. Hold on. Oh my gosh. Yeah. Who would put that music to Newton's Cradle? Not me. Okay, so let's do away with that. Unfortunately, you missed the clicking and the clacking. But you can see the person here is just pulling back these spheres. And what's fun and surprising about it is they're demonstrating the conservation of linear momentum. When one of the spheres crashes into the other, they transfer momentum. And you can actually sort of analyze and predict all of this motion using the equation of momentum before you even see it in action. The calculations for momentum allow us to analyze car collisions. They especially help us to analyze the collisions between protons in the Large Hadron Collider to learn about the forces of nature. And basically, if you've ever played a game of pool, you know that linear momentum is why when you're playing a game of pool, the cue ball will come to a rest and the 8-ball will begin to move when they collide with each other, because you've transferred momentum from one object to another. In the 1800s, physicists who thought of momentum actually thought of it as kind of like a magical fluid that would pour between objects. So if you had a particle and you caused it to collide with another particle, the transfer of momentum was like a magical fluid that would go from one particle to another. In general, when you analyze momentum collisions, you find a couple of interesting things. You find if the masses of the two objects are equal, then usually the first particle, the incoming particle, when it collides, will perfectly come to rest and transfer the momentum to the other particle. This is how Newton's cradle works. It works because the particles that you see there are equal in mass. And so one particle comes to rest while the other particle gains the momentum of motion. Other possibilities during momentum collisions are what happens when you have a BB and a bowling ball, right? So if a BB, a low mass particle, should hit a high mass particle like a bowling ball, usually when it collides with it, it bounces off and moves in the other direction. Another possibility is also a collision between a BB and a bowling ball. But if a bowling ball hits a BB, it will push it forward and it'll just snowplow the thing into motion. Those are the three extreme cases where one particle is much more massive than the other, or when the two are equal in mass. And that's what's cool about momentum. It's sort of abstract, but you can use it to predict what happens when things collide with each other. Most people have an intuitive sense of linear momentum. What's interesting is momentum takes on a weird and sort of buggy feature when you actually make things start to rotate. Rotation makes things inherently more complicated. So let's talk about another quantity, a quantity called angular momentum. Rotation is complex for many different reasons. Anytime a system begins to rotate, all of your physics concepts like force and momentum take on a kind of new bizarro twist to them. We define L as the variable for angular momentum. And usually the setup, I think a little diagram would be helpful here. The sort of, excuse me, while I call up the, I want to get rid of this thing here. While I call up the right slideshow. There we go. Here we go. This is the setup that we want to consider when we consider angular momentum. You have a particle attached to a string, and you're sort of spinning the particle around on the string. The string is pinned to the table with a nail, and your particle has a mass, it has a velocity as it travels around in a circle, and it has a radius of orbit. Sometimes we call this the moment arm or something. And that radius of orbit is the circle around which the particle is spinning. This particle clearly has momentum because it has a mass and a velocity, and if I multiply the two, I'll get momentum. But it's constrained to move along this radius, and it now develops a property called angular momentum. And the definition of angular momentum is a particle's mass times its velocity times the radius of orbit. Like linear momentum, angular momentum is a conserved quantity. And one of the concepts behind angular momentum is something like this. It sort of means that objects that rotate want to keep rotating and in the same direction. The direction of linear momentum is obvious. When you have a particle and the particle travels with some velocity, the direction of the momentum is the same as the direction of the velocity. They're in the direction of the particle's motion. But angular momentum doesn't work like that. And one of the reasons why is when something rotates, it's constantly changing its velocity direction. So I can use my little drawing tool here to explain this. When the particle is here, the direction of its velocity is like so. When the particle is over here, the direction of its velocity is like so. When the particle is over here, the direction goes. It's constantly changing the direction. But if you think about it, what does not change is the axis of rotation. So although it's kind of a goofy concept, we define the direction of angular momentum to be along the axis of rotation. And the conservation of angular momentum has some sort of buggy consequences that I can share with you in this fun little demo here. So let's see if I can do this half decently in my apartment. I'm just going to push this back. I have a wheel, which I sometimes use to demonstrate angular momentum, okay? It's just a normal bicycle wheel with some handles on it. And I've got a little string here, okay? When I hold the bicycle wheel up by the string, you can see the bicycle wheel just kind of flops over. Gravity just tries to flop it out of my hands. Do I want to stand on the stool for this, or no, I'll just angle the camera down. Okay. So what I'm going to do is I'm going to give this guy some angular momentum. I'm going to give it a spin. Now remember, the direction, because the wheel has particles of mass all along the rubber rim there, there's a lot of mass moving around in a circle, and the angular momentum is directed along the axis of rotation, which is towards you, the observer, okay? And I'm going to give this thing a spin, and I'm going to hold it by the string, and you will observe that gravity is unable to pull the wheel over. In fact, let's see here. I'm going to angle this up. The wheel undergoes a motion called precession, which is related to the precession that Earth goes through. Watch this. If I hold this thing and I can try to knock it over, the conservation of angular momentum won't let me do that, right? This is why you don't fall off your bicycle when it's in motion, but you do when it stops. This is the principle behind gyroscopes. We use this to point and orient telescopes in space. This is why, I don't know, you guys, what are those? I actually have a genuine question for you guys. When I'm on the bike path, I see all these kids riding this like single motorized wheel. It looks like a hoverboard or something. You step on each side and there's a big, what are those things called? Do any of you own one of those? I keep saying ding-a-lings. Does anyone know what I'm talking about, or do I sound crazy? They're called a one wheel, Caroline? Yeah. This is what, we live in a world where there are one wheels now, and this is why people don't fall over when they're riding their one wheel. Okay, and is that the brand name of it, Caroline? Like if I type that into YouTube. This is, yeah, exactly, okay. Let's just watch some ding dong riding his one wheel, okay? He's using the conservation of angular momentum, so once this wheel's going, it keeps him aloft or keeps him upright. I was hoping we could see a video of him flying down the sidewalk here. Well, it might be that my internet connection can't really handle streaming YouTube at the same time it's streaming video to you guys. Oh, no, or maybe I just have to hit play. Okay. Geez, guy, get a move on here. Yeah. So I see these people on the bike path all the time. I guess that wheel is pretty thick too, so that probably helps with your balance. Anyways, a bicycle is probably a much better analogy. The conservation of angular momentum has some weird and buggy results. It's not intuitively obvious that when you hold the wheel by the string, gravity will be unable to push it over. That's a sort of surprising result. Now, how does that relate to Kepler's second law of planetary motion? Well, let's analyze the image that we looked at earlier. Oops, sorry. Let's get rid of this guy here. That was not the jazzy YouTube video I was hoping it was going to be. In Kepler's second law of planetary motion, which I have here in slide 69, function F5 69, you can see that as the planet gets closer to the sun, its radius of orbit here is shrinking. Correspondingly, the velocity of the planet must move faster so that it can whip around the sun and conserve angular momentum. As the planet gets farther and farther from the sun, the radius of the orbit gets longer. To conserve angular momentum, the velocity must slow down. And you can see that in the crummy animated GIF I have here. The planet's moving faster at perihelion and much slower at aphelion. It's one of the reasons why, for instance, Halley's Comet has a period of 76 years. It spends most of that time out at the edge of the solar system near the orbit of Neptune. And when it does come around, it's only around for several months at best. Angular momentum is a really important concept in astronomy because everything is in rotation. Earth is spinning on its axis. It revolves around the sun. The sun is revolving around the center of the galaxy. Angular momentum is the reason why solar systems flatten into disks. It's the reason why some galaxies flatten into disks. And it's just a concept that we might want to invoke at some point. Angular momentum has some abstract properties to it, right? And we can analyze the units of this if we wanted to, right? This actually might be a quick, worthwhile thing to do. For linear momentum, P, you have a mass times a velocity. What are the units of linear momentum, students? What are the units for mass? Come on, someone play with me here. What are the units that we use for mass in the MKS system?
Kilograms.
Okay, how about velocity?
So meters per second.
That's right. So the units of linear momentum are kilogram meters per second. You might compare that with forces. So earlier, Austin tried to describe momentum as a force. Austin, the units of force are kilogram meters per second squared. Slightly different, okay? For angular momentum, the units are almost the same, but now we have to multiply by another radius, which has units of meters. So the units of angular momentum are kilogram meters squared per second. What the hell is that anyways? Kilogram meters squared per second. That's not an easy concept to wrap your mind around. It's abstract. But momentum is a powerful concept because it is a conserved quantity. The total angular momentum in a system must stay constant. You know, the moon is slowly drifting away from Earth in its orbit, and it causes the Earth to spin down and the length of a day to stretch out over time. I think we lose a second or a fraction of a second every 100 years or so. The length of a day is slowly increasing over time. That's kind of a weird thing to think about. Okay, it's because of the conservation of angular momentum. Let's talk about some other abstract quantities that come up in physics. And I'm thinking about energy. So let's go there next. Can I erase this, students? I'm going to do that. Oh, actually, there's one last thing we need to do before energy. I need to have a quick discussion with you about a formula that we used in our office hours last time, and that's the concept of escape velocity. We had a single problem on this, but I want to introduce it formally in our lectures. The escape velocity is a concept that Newton came up with maybe in the following way. I want to show you guys a quick picture here, if I can find it. It's a picture of a cannonball being fired around the Earth. Here it is. And this is probably how this concept developed. Newton's laws of motion, his understanding of forces and his understanding of momentum allowed him to calculate the distance that a cannonball would fire before it fell to Earth, right? So you fire a cannonball horizontally and it sort of drops down. Actually, it's kind of a legendary physics exercise that I had to do as a student, where you do a sample problem where a soldier fires a bullet from a rifle that's perfectly horizontal, and they fire it at maybe 300 meters per second or so. And at the exact same moment, you drop a bullet, you just drop it to the ground from the same height as the rifle. And before you start solving the problem, you think your goal is to calculate how long does it take before the bullet that you drop falls to Earth, and how long does it take before the bullet that you fire horizontally drops to Earth. At first, you're under the faultiest notion that because you're firing this bullet sideways, that it will for some reason be up in the air for a longer period of time. But when you analyze the problem, you find, despite that the horizontal bullet is traveling a much further horizontal distance, it has the exact same amount of time in the air. So if you fire a bullet from a gun, that's it. That's the time it takes for it to travel whatever distance it travels before it strikes the ground. When you do this problem, when Newton did this problem, he discovered that the horizontal motion of a bullet is completely independent of the vertical motion of gravity pulling it down. It's almost like there's two separate things happening at once. There's its sideways momentum, its sideways direction of motion, and then there's its vertical motion controlled by gravity. And if you keep meditating on this concept, you realize that if you fire a cannonball out of a cannon, it will travel farther and farther the faster and faster you travel it. The faster and faster you fire the bullet. So you fire it at one force at one velocity and it travels this far before it hits the ground. You fire it a little bit faster and it travels that far. Now, if you are on a planet like Mercury, or if you were on the moon where there is no atmosphere, at some point there would be some critical speed at which you fire the bullet and it's traveling so fast that it would actually miss the curvature of Earth and then it would go into a low Earth orbit, and it would travel, or a low Mercury orbit. It would travel around the planet, and then boop, it hits you right in the back of the head. Okay, and this velocity is called the escape velocity. It's this one critical speed at which you will pass the curvature of Earth, and as long as there's no air friction, you'll actually go into a sort of low Earth orbit. So in theory, if you were on the moon where there's no atmosphere, you could fire a cannonball fast enough where it would orbit just a few meters above the surface of the terrain of the planet. Introducing the escape velocity, which I will give you a symbol for, V subscript ESC. And we can define it as that unique speed that any object, it doesn't matter if it's a rocket ship or a bullet or an eraser or a tennis ball, that unique speed that any object needs to escape the gravity of a, here I'm going to put this in quotation marks, I'm calling it a planet, but really it could be a star or any kind of spherical thing, a spherical space station, whatever, to escape the gravity of a planet of mass M, capital M, and radius capital R. Usually the crummy cartoon picture that we draw for the escape velocity is we have a sort of circular planet or star. It has a radius R and a mass M. And then you have some object like a rocket, and you're trying to fire that at the escape velocity of the planet, all right? As you learned last time, the formula for the escape velocity is pretty simple. The square root of 2 times g times the mass of the planet divided by the radius of the planet. There's your formula. I think it would be worthwhile to do a sample problem here. We only did one calculation for escape velocity. The escape velocity turns out to be kind of a measure of how strong the gravity of a star or a planet is. And we're going to use it quite a few times in this class. So I'd like to do a sample problem up here. Class, may I erase this bit up here, the text? Any objections? All right. Let's try a quick sample problem, okay? Find the escape velocity of Earth. Earth has its own unique escape velocity. We're going to need some data. The mass of Earth is 6 times 10 to the 24 kilograms. And the radius of Earth is 6,400 kilometers. Hey, Arunsak, am I ready to plug these numbers into my escape velocity formula?
You got kilograms, you have kilometers. Don't we need meters?
Yeah, that's my point. So let's put that note down here in our notebooks. The mass has to be in kilograms, and Arunsak was able to figure out that the radius should be in meters. That's a MKS formula right there, okay? So Arunsak, help me out with that. I know you're good at dimensional analysis. Can you help me quickly convert 6,400 kilometers to meters?
Yep, so write down 6,400 km,
Okay.
X bar,
Yep.
and then units, you got km on the bottom, and then meters at top, and you have your conversion,
And do you
which
know the
is
conversion?
1,000 over 1.
Yep. Can you do
And
it
then
in
you
your
just
head? Look how good it is, guys. That's why I called on him. You don't need a calculator. Just how many zeros you got?
6.4 to the 10 to the 6, right?
Very good, yeah. Because you've got 5 zeros, right? 1, 2, 3, 4, 5 zeros, but the 4 also gets treated like a 0 because the decimal place moves 6 times, right? Okay, so Arunsak did that pretty quick. Hopefully you guys can do it that quick as well. Now let's try plugging it into our formula, all right? Okay. The escape velocity of Earth is the nice big neat square root of 2 times big G, which is always 7 times 10 to the minus 11 meters cubed per kilogram per second squared. Okay. Times the mass, 6 times 10 to the 24 kilograms. Divided by the radius, which is 6.4 million meters. Sorry, I'm trying to use blue for units, but I was getting a little distracted there. Okay, students, punch that up. Make sure you still got some good calculator skills. Punch it up, tell me what you get. Caroline, what you got for me? Christopher, I'm having trouble seeing that, buddy. You got to make it more perpendicular to the camera. Arunsak, that's definitely wrong. I think you forgot to square root it, buddy. Chris, hold it up. Chris, you got it. Chris has got it. Who else? Arunsak, Emily, you got it. Anyone else? Chris, you're a little off to the side and there's, oh, yep, you got it, Chris. Christopher, nice job. Caroline, something went wrong. Try it again. I actually have some iced tea, but to be honest, I drank a lot of coffee and it's not helping. So I need to atone for my sins here. Okay. Maybe for the benefit of the night students, I better punch this in for you guys, huh? I guess that's what I need to do. This is just for anyone else who's having trouble. It's good to see if you can get it without my help first. Okay, let's do this. Caroline, you want to watch me or? 2 times 7 exp negative 11 times 6 exp 24 divided by 6.4 exp 6 first equals, then shift square root. What's my answer? Class, what's my answer?
$11,456.
Well, that's a lot of sig figs, Christopher. Can you round it to 2 sig figs for me?
Sig figs?
Yeah. Yeah, Arunsak, 11,000. What are my units, Arunsak? Christopher, The other numbers that were there, they're not real. They're just garbage numbers. You only have like 1 or 2 sig figs of precision here. So the 4, 5, 6, it just doesn't mean anything. It's not real. The 11 part is real. The 1,000 part is real. I'm sorry, what were the units?
Is it meters per second?
Correct.
Okay.
Because it's an escape velocity, it's going to come out in MKS units of meters per second, but it's customary to convert your escape velocities to kilometers per second. That's considered a classy thing to do. So what would this be in kilometers per second?
1.1?
No.
No, 11.
11, right. So you can actually multiply meters on the bottom, kilometers on top, right? 1 kilometer is 1,000 meters. And if you divide, so you have your per second, you cancel out meters, you end up with 11 kilometers per second. "11 kilometers per second is the escape velocity of Earth. Is that slow or is that fast? How many miles per hour do you think that is? Let's ask Mr. Google, okay? Let's do 11 kilometers per second to miles per hour. Is that fast? That's 25,000 miles per hour. Anything that travels at 25,000 miles per hour or 11 kilometers per second travels fast enough to escape the Earth. Hell, if you could chuck this dry erase marker at 25,000 miles per hour, I could literally throw it into an Earth orbit. It turns out that if you actually watch a shuttle launch, all right, or a rocket launch, it's not so easy to do this. And that's because to get the thrust, to get something moving that fast, you actually have to have this big tube full of some oxygen booster fuel to actually thrust that thing and get it moving up to 11 kilometers per second. So, I don't know. Let's watch the few seconds of this rocket here blasting off. So when you launch a rocket into space, most of that big tube is just full of fuel. And it's full of fuel so you can get this thing up and running, and you can provide enough thrust to go from 0 kilometers per second up to 11 kilometers per second. It turns out that as you add more fuel to your rocket, you add more mass, and therefore you have to add even more fuel in order to get this thing moving fast enough. And it becomes this sort of tricky calculus problem where you keep adding more fuel to get more thrust, but the fuel adds more mass, which requires you to have even more fuel. And from the state of our current rocket technology, I think the whole thing kind of tops out somewhere around 10 kilometers per second. We can only get most of these rockets moving up at a speed of about 10 kilometers per second. And therefore, that should not be fast enough to leave Earth. Now, if you watch these things as they blast into space, the rockets kind of seem to take this left-hand turn. Let me see if I can show you another picture here of a shuttle launch. There's kind of a cool photograph of a rocket being launched, from the cockpit of an F-15 fighter. It's this, oh, what do they call it? The tilt shift? Yeah, if you watch these rockets as they blast off of the surface of Earth, after the rockets are fired up into the atmosphere, they sort of curve and, oh, come on. That's lame. I was just hoping to show you a picture like this, all right? Notice, for instance, that this rocket, after it's been fired off of the ground, is kind of curving up and to the left. It turns out that one of the reasons we can get rockets up into space is because if you're standing on a spinning Earth, you actually have a non-zero velocity through space. At the equator, in 24 hours, you kind of just do this, right? But as you go down lower and lower in latitude, you are traveling a successively bigger circle in a period of 24 hours. And it turns out that somewhere right down here, about the latitude of Cape Canaveral, Florida, if you calculate your velocity through space by dividing the circumference of this circle by the 24-hour rotation of Earth, your velocity is pretty darn close to 1 kilometer per second. So the way that we get these rockets into space is we actually don't fire them straight up off the surface of Earth. We fire them at 10 kilometers per second into the direction of Earth's rotation, and the rotation of Earth gives you the last 1 kilometer per second you need to actually get into escape velocity. So human beings can just barely make it off the surface of their planet. Exactly, Christopher. Christopher, what if Earth had been twice as massive or something? What if we had been born on a planet with a little bit more mass? We might not have ever made it to the moon. That's also something to think about for all you, yeah, it's cool. It's also something to think about for all you travel to Mars enthusiasts like Elon Musk. When you think about the Mars One program where they want to send people, no, Austin, the moon landing is not fake. The moon landing is definitely not fake. There's, there's too many people involved in a scientific enterprise like that.
I think it was like thousands of people involved, so there's like no
yeah,
way
there are
they
lunar
could have
rock
kept it
samples.
quiet.
You can talk to the astronauts that went up there. Many of the reasons, I usually get this question once a semester. Well, Cole, you don't have to believe in anything. You know what I mean? Like, people just invented germs to sell you soap. And while you're at it, why brush your teeth? You know, like, come on. If you want to be like that, then you can live your life like a paranoid schizophrenic, but it's not going to do you any favors, okay? Who do you believe? You believe Google? You believe President Trump? I don't know. You know, like, there aren't many trustworthy things these days, but the moon landing is definitely one of them, okay? So that's something, that's a happy thing. In any case, oh gosh, I totally got sidetracked there. If you want to go to Mars, okay, I'm not going to go there, Austin. By the way, the living in a simulation thing, there is a branch of physics called digital physics. Some people do really believe, and they have scientific arguments for why reality could be a simulation. So the Matrix might not be as far-fetched as you might think. But look up digital physics. I don't have time to go off on a tangent on that now. If you want to go to Mars, it's one thing to get to Mars and even land there, but there's no Cape Canaveral, Florida, and there's not enough oxygen. Well, it would be difficult to harvest the oxygen that you need to make a solid rocket booster. Getting to Mars is technically feasible. The hard thing would be getting off Mars if you decided you were bored and wanted to come home. So you've got to think about your trip to Mars very carefully because it could be a one-way trip. I'm almost out of time, but I have like a few more minutes left, and I've got one more module to do with you guys. It's a module on energy, okay? Energy is a concept that comes directly from Newton's laws of motion, and it's similar to momentum in that it's an abstract conserved quantity. We will have that 10-minute break, Austin, I promise you. Energy is an abstract quantity that gives us insight into how physical systems work. So let's do a little set of notes here on energy. Okay, so energy, if it's properly defined, has a sort of abstract definition. It is a force that is multiplied through a distance. And at the end of the day, this is what the fundamental definition of energy is. We define energy as such, so I could use a triple equal sign. Unfortunately, although this is the true definition of energy, at your state of development, this definition is not helpful. It's not helpful because it's a little too abstract and it doesn't explain what's going on here. Here are some things we can say about energy. Energy takes various surprising forms. It can be converted from one form into another form in a similar way to the way momentum can get transferred from a cue ball to an 8-ball. This magical thing pours from one object into another. Energy can kind of flow between systems. And there's a certain set of classes of energy. Some energies are called potential energies. Some are called kinetic energies. And there are other forms of energy which are not exactly potential and not exactly kinetic. One that I'm thinking of in particular is that light is a unique form of energy that has aspects of a kinetic energy and aspects of a potential energy. So light is kind of a unique form of energy. There are others as well. In fact, it's going to turn out that later on when we study relativity, heat, Cameron, is a separate, yes, heat is a separate discussion we're going to have, Cameron. Heat is related to kinetic energies. For now, Cameron, I'll just tell you that heat, since you were clever enough to ask me about it, thermodynamic energy, Cameron, is usually kinetic energy. Heat is a transfer of energy. I might have to get to the heat thing next time because I'm going to have just enough time to do some potential and kinetic energy. Well, Donovan, I wouldn't say it like that. I wouldn't say everything is going to turn into heat. But I could say this if I wanted to, Donovan. Everything already is energy. You'll remember that Einstein is famous for coming up with this legendary formula, E equals mc squared, where c is a constant of nature called the speed of light. Because the speed of light does not change, this formula teaches us that mass itself is a form of energy. So Donovan, suppose I want to go along with you there, right? Let's think about the entire universe after the Big Bang. There are atoms and there are photons. The atoms eventually cool into stars and galaxies. The photons keep bouncing around. New photons are generated. The photons, which are particles of light, they're energy, and the mass particles are energy too. So you can think of the universe as kind of being like three things, or maybe even just two things. There's space and time, which are kind of connected to each other. And then there's mass energy, which is connected to each other. You might think of space-time as being like we could make an analogy, where is it here? People keep moving my stuff. Someone challenged me to a game of chess the other day. You could think of it as being like a chessboard, where space-time are the grids or the checkers of the chessboard, and the mass energy are like the pieces that move around. What would the forces of nature be then, Donovan? The forces of nature are not space-time, nor are they mass energy. The forces of nature are the rules by which the pieces move. If you've ever been a chess enthusiast like me, you know every piece has its own particular movement. The knight goes 1, 2, and over, right? Well, the forces of nature govern how the particles move. So the forces are like the rules, space-time is like the board, and the mass or the energy are like the pieces. Oh, what? I love me some Chinese checkers, okay? Cameron asked about Chinese checkers. I'm a bit gamey. I like my board games, okay? Anyways, listen, before I go off on a totally wacky tangent, sorry, a tree branch just scraped my window and I didn't know what was going on. With that in mind, Donovan, I wouldn't say everything is going to turn into heat. I would say everything is energy already. Sometimes people talk about the eventual expansion of the universe as being a heat death, because eventually all of the particles will move far apart enough where no new stars can form. And when stars eventually die, the universe will be kind of a cold, lumpy distribution of matter. So heat death is something that we could talk about eventually, Donovan. Let's save that. For now, what you guys need to do is you need to build up some intuition about energy. And a good way to do that is for me to introduce you to potential energy, gravitational potential energy, and maybe tell you a little bit more about this. In our next class, I'm going to get into heat and light and atoms. But let's just do one or two more modules, maybe one more module before we stop here. I want to introduce you, one last thing that we need to say about energy before I do potential energy. Energy is a conserved quantity. This is important. You may have heard of this before as the conservation of energy. A conserved quantity means the total energy in a closed system, such as a box or such as an oven or something like that. The total energy of a system is constant. And that means if you allow yourself to think in terms of energy, you can predict what will happen to a system over time and how it will evolve. Let's start off with a basic example called gravitational potential energy. Gravitational potential energy, when I'm feeling lazy, I just call it potential energy, is the energy stored in a gravitational field. Or I've used some abbreviations there. That's gravitational. All right, you know what? I'm not going to do that, because people get confused when I do that. And I'm going to erase this little bit here, okay? It has a kind of setup associated with it. Usually you have the ground, and then you take some massive objects like this 1 kilogram mass, and you lift it up from the ground. So I'm going to take my 1 kilogram mass, and I'm going to suspend it some height h above the ground. Okay, so I'm basically just lifting it up. And when you do this, you store a form of potential energy called gravitational potential energy. The formula which describes it is mass times little g times h. Class, reminds everyone what little g is. Remind me what little g is, so that I know you know what I'm talking about. What is little g?
Isn't it Earth's gravity?
You wouldn't say it exactly like, well, kind of, yeah. What's the value of little g?
Can't remember.
Anyone? I did do a lecture.
9.8 meters per second.
Not meters per second. It's approximately 10. But it's not meters per second, because meters per second is a velocity. The units are meters per second squared. And this bad boy is technically known as the local acceleration of Earth's gravity. The acceleration of Earth's gravity. So someone said Earth's gravity, and that's kind of a loosey-goosey way to say it. It's an acceleration. That's important. It always has the same value. Okay, so let's just think about what this energy is then, right? So this morning I had some oatmeal for breakfast just before class started, and I gave my muscles some energy here, some big muscles, big energy. And here's this 1 kilogram mass. We're going to put it down on the ground, okay? And let's go ahead and let's make some energy. I'm going to take a couple meter sticks here, and I'm going to hold them maybe 1, maybe 2 meters above my head. Whew. You guys are a little close to me right now, because there we go. And I'm going to lift up that 1 kilogram mass. And I pull it up over my head. I'm going to fight against the force of gravity. I'm fighting gravity right now, and boop, there it is. I have lifted a 1 kilogram mass 2 meters above my head, and I have stored some energy. Class, where's the energy? I don't see anything. I was wondering if you could tell me where the energy is hiding. I want to understand what energy is.
In your arm?
Well, originally it was in my arm, but if I wanted to, Austin, I could hook this up to a little string and just suspend it. That's probably what I should do. I should have a little string and a magnet, and I could just hook it to that string, and I could remove my arm. Where would the energy be then?
Right where your fingertips are?
No.
Not exactly.
Would it be in the weight?
At first you'd think so, but that's not exactly true either. The energy isn't hiding inside the weight. It's not really hiding inside the Earth. and the energy isn't hiding invisibly in the space in between. The energy is stored in the system, the complete system, which consists of the mass, the distance, and the ground in between. And one way to see this, students, is for me to show you another type of potential energy. Not all potential energies are Yeah, Austin. Well, Austin, I'm going to try to explain what I mean by that. Not all potential energies are gravitational. Here, I have a string, like a slinky, or it's just an intense string. Strings obey this law in physics called Hooke's law. And in Hooke's law, the string has a natural equilibrium, a natural resting point where the spring is happy. And if you take the spring and you stretch it, the spring tends to want to do this. It wants to snap back. We all know that about springs, right? In physics, we learned that there's a law called Hooke's law that tells us that the force that the spring will snap back with is proportional to how much you stretch the spring. So if I stretch it this much, I'll get a little force pulling it back. But if I stretch it more, the force becomes more intense. When I take the spring and I stretch it, and I fight against the string, and I hold it like this, I am storing a type of potential energy called, I guess you'd call it electromechanical potential energy. The potential energy is bound up in the coils of the metal, which want to be back here in this position. And all along the spring, those coils are fighting against my hand, and they want to return the spring to its equilibrium point. But if I keep fighting against them, I'm storing energy in this spring, and I can do something useful with it. For instance, I might, I don't know, put a little acorn on the end of it and fling it at my kid brother's head or something, okay? I could do something useful with that potential energy. It's easy to see where the energy is being stored in the spring because all the coils of the spring are simultaneously trying to return it to equilibrium. It gets harder to see with gravity because gravity is kind of like an invisible force. In other words, what I'm saying to you, Austin, when you said, what does that mean? In some ways, this 1 kilogram weight is a lot like the spring, right? I'm pushing this against the will of gravity, against the force of gravity. And once I store the potential energy, like the spring, the mass wants to snap back to Earth, right? And I can do something with that potential energy. I could take it over to a small village in, you know, some destitute part of the world, and I could drop it out from an airplane and I could bonk someone on the head with it. And that's how I could use that potential energy, okay? Maybe not an ethical use, or a moral use, but we could do that if we wanted to. In any case, this is similar to the spring. You're keeping it and preventing gravity from sticking it to the ground. Why don't we go ahead and calculate the value of that energy using the numbers that I just had here? Remember that I had a mass whose value is 1 kilogram, and I suspended it a height 2 meters off the ground. And since I did this demonstration on Earth, our local acceleration of gravity is 10 meters per second squared. So let's go ahead and let's calculate this value of potential energy. In that example, the potential energy would be 1 kilogram. Here, let me use this red marker, it's a little better. 1 kilogram times 10 meters per second squared times 2 meters. Okay, class, I'm going to do the hard part, which is the math. 1 times 10 times 2 gives me 20. I want you guys to tell me what my units of energy are.
Kilograms meters squared per second squared.
Lovely. As you can see, this is a little bit of an abstract concept, kilogram meters squared per second squared. What we usually do here is we define this as a new unit to hide the confusion that comes with all of these letters. We call this 20 joules of energy. 20 joules. Sometimes you just express it as 20J. So the fundamental units of energy, this will be my last point for the day because I'm out of time. The units of energy, 1 joule, is defined as 1 kilogram meter squared per second squared. And energy can take various forms, from potential energy to kinetic energy. We'll have to, it's kind of a big topic, and I realized I've kind of done bad today with this lecture, so I didn't make as much progress as I wanted to. Let's pause there, guys. Remind me to pick up with joules and energy next time. Austin, you said you wanted a little break, right?
I do.
Everybody like that idea? Okay. 10 minutes? All right. Okay, let's do that. So we'll take a 10-minute pause and then I'll come back. Our lab today, I don't think you need anything special. We're just going to do a calculation together. You need a ruler, a paper, a compass if you have one, but papers and pencils and rulers. Stacy, it's not that important. If you don't have a compass, you can freehand it, but if you do have a compass, that'd be cute. Okay.
If you have an iPhone, you have a compass, just to.
No, I mean like, I don't mean that kind of a compass. Hold on. I mean, geez, I'm having a day where I can't find anything. I mean a drawing compass, Donovan, right? Not like north, south, east, west. I mean like a pencil and a sticky, right? I mean like a drawing compass.
Sorry.
But it's not that important. Why don't you guys just take a break and we'll come back in 10 minutes, okay? Okay, back by popular demand, it's unsweetened iced tea. Let's move ourselves over to the lab situation room. I'm just going to pause this for a second while I get the equipment set up for the benefit of people watching later. Sorry, I'm going to resume that recording. I realized I didn't include that. If you have a circle maker handy, great. You're going to need a pencil, some erasers, some notebook paper, maybe a compass if you have one, calculator. But honestly, pencil, calculator, and paper will be fine. Because of its importance in this class, the goal is to spend some time working with Newton's version of Kepler's third law. Now, I'm a little actually ahead in this class of where I normally am, although today I kind of got off track a little bit, or I went too slow rather. But normally this lab is a chance for us to try Newton's version of Kepler's third law together, and for us to do the calculations slowly, carefully, to make sure that everyone who is willing to video chat with me can actually punch this into your calculator. I've got some high hopes that you guys can already do this, so this actually should be a pretty smooth ride. But remember, we are going to have to do this on our exam, and our exam will be coming up in a week or so, right? So I know it's not fun. Since this is one of the harder formulas we use during the semester, it's probably a good idea for us to practice it slowly and carefully. So let's talk about the point of today's lab. The point, for starters, is to calculate the period of the International Space Station. And let's just rap about that for a second, all right? So if I type ISS into Google, the first thing that comes up is the website for the International Space Station. And the International Space Station is pictured here. It's a joint collaboration between NASA and the European Space Agency, and a number of other space organizations around the world are part of this collaboration. And it's staffed year-round by astronauts and cosmonauts from Russia, Japan, the US, the European Space Agency. And people live up here on the International Space Station, and they do experiments in all kinds of sciences: physics, biology, astronomy. They maintain a pretty cool YouTube page. I think it's Chris, is it Hadfield? Is one of the astronauts. And they even tell you what life is like every day on the ISS. These cool YouTubes, you can watch Chris Hadfield teach you how to do everyday things on the International Space Station. Here's one where he teaches you how to brush your teeth in space.
Your teeth in space.
It's always more complicated.
Standard toothbrush, nothing magical there.
And
we got a few different things.
You know, it's kind of cool just because you can see, you can imagine how cool it would be to be up here in the ISS and how much fun it would be if every day your life was a big physics experiment, you know? So look at this guy, he's pushing out the blob of water. And that's one of the things about brushing your teeth in space is without gravity, all these things that you take, you don't even think about how they benefit you. You've got to sort of use the molecular cohesive forces of water to get it to stick to your toothbrush there. That's pretty wild if you think about it. Anyways, I don't know if you guys have ever seen the International Space. Oh, he shakes a soda and nothing happens. Oh, that's great. I haven't seen that one, Daniel, but I have to go and. So you've seen this, Daniel. You're a fan of Chris Hadfield's videos. If you find the link to that, why don't you send that to the class, Daniel, while I'm rapping? I'm sure everyone would like that. I like the one where he wrings out a towel in space, but the water doesn't go anywhere. It just kind of sticks to the towel. It's pretty wild. In any case, I don't know if you guys realize this, but if you go out at night, you can actually see the International Space Station fly overhead with your naked eye. Has anyone, out of curiosity, seen the ISS pass overhead? It's like a thing that enthusiasts do. He was in the ocean floor. Huh, okay. That's all right, Daniel. In any case, but have you seen it, Austin? That's the first question. Oh, you don't know how to tell if it's the ISS. The way you know it's the International Space Station is it's really bright, like sometimes almost as bright as a planet. And you'll see the thing moving extremely fast. You can tell that it's much too high up to be an airplane. It just looks like a bright star that is hauling ass across the sky. And sometimes it's only up for a matter of 3 minutes at best. But it looks like an insanely bright. You can see many satellites at night. They look like little stars that are just moving across the sky. But the ISS is very, very bright. Well, that's kind of the point of today's lab, Austin, is to use something we know from our class, like Newton's version of Kepler's third law, to calculate the orbital period. And that's going to tell us how often we can expect it to come by overhead. And I'll eventually get around to answering your question, Austin. But first, why don't we try to calculate the period of the ISS? That's our job. Let's see if we can do that. I'm going to try to, excuse me, share my screen here. Let me activate my Wi-Fi if it's not already. Okay, that's active. So let me, let's calculate. Let's get to it. All right, so I'm going to share my screen. And here we go. That seems to be working today, thank goodness. And let me adjust this light here. My camera phone sometimes has these weird lines on it. I don't know how to fix it exactly. Okay. All right. And I'll use this. Well, I'm going to push you guys back for a second here. This holder here. Let's take off portrait lock. Okay. So make sure you start off, let me sharpen my pencils here. Sharp pencils, sharp minds, okay? So make sure you start off by putting your name. Let's put lab number 4. And the lab is finding the period of the ISS, okay? So first thing we're going to want to do is we're going to draw a nice diagram of what's going on. Here are the givens that we are going to be allowed to work with. So let's pretend this is a test question. Wink, wink, nudge, nudge. Let's pretend this is going to be a question that's on the test, okay? If so, you might have a situation where the givens are something like, okay, I give you the mass of the Earth. The mass of the Earth is 6 times 10 to the 24 kilograms. And I'm going to give you the radius of the Earth. The radius of the Earth is 6,400 kilometers, all right? And I'm going to give you the mass of the International Space Station. It's 400 metric tons. Does anyone know what a metric ton is? How many kilograms in a metric ton? Take a guess.
1,000.
Very good. Good guess. So if it's 400 metric tons, that's 400,000 kilograms, roughly is the mass of the ISS. I got that from Wikipedia. And the orbital height of the shuttle, its altitude is, I believe, 400 kilometers above the surface of Earth. So what we want to do is we want to draw a diagram. Drawing a diagram is a really, really smart idea. And the higher the quality of your diagram, the better you're going to be able to see the relationships between these variables. So I could use a circle maker, honestly, but I guess I'm showing off a little bit today, so I want to show you guys how to use a compass, okay? So let's sort of, I don't know, we'll set the diameter to be something like this. Doesn't really matter. I'll just sort of pick a radius. Let me just make, yeah, okay. So I'm going to lean and spin. I'm going to go around a couple of times here. I could use my circle maker as well, but felt like using my compass. Okay. A beautiful, perfect circle. And I'm going to mark the midpoint with a little dot where the poker part went through. I'll take out a ruler and I'll, excuse me, draw on the radius. Yeah, the radius is about 3 or 4 centimeters, okay? And I'll label this as the radius of Earth, which you guys know is 6,400 kilometers. By comparison, the height of the shuttle is only 400 kilometers. So I'm not really going to be drawing this to scale, but I'll try to keep the sense of the perspective. I'm going to make sure the height of the shuttle is a lot smaller than the radius. Like I said, this is just to scale, but it's something. Sometimes when you want to draw a satellite or a shuttle, you kind of just make a box and then you put some solar panels on it, okay? This is kind of like a satellite, more than the International Space Station, but my artistic skills are somewhat limited, so there we go. And our goal is to find its period, how often it orbits around the planet. Let's start by writing down our NK. By the way, you guys can see why this is tailor-made for Newton's version of Kepler's third law, right? We could not use p squared equals a cubed for this, because just like I told you in the story today, when Galileo wrote to Kepler about the orbits of Jupiter's moons, p squared equals a cubed didn't work for that. P squared equals a cubed only works for planets going around the sun. We need us some NK3 to solve this problem, okay? And let's just write down our NK3. P squared is equal to 4 times pi squared times a cubed over g times the sum of the masses, which in this case is the mass of Earth plus the mass of the International Space Station, okay? Let's first try to identify our A. Do you guys see what we're going to be using here for A? So here's the height.
The height.
I was worried that you might say that. Christopher, I understand why you said the height, but remember the shuttle is, let's see what the chat says. Okay. Blair is appreciating my artwork here. Thank you, Blair. And Blair has another suggestion. Remember, Christopher, the shuttle isn't orbiting this point. Wait a minute, sorry, my phone just crashed here. Just a second. I got to turn off the timeout here.
I think I get it. It's like orbiting the center of mass, not the surface of the planet.
Yeah,
Right.
and since this is negligible, like the center of mass is basically right there, right? And that's right, Christopher. That's a nice way to say it, the center of mass of the system. You remembered some stuff from lecture. That means the A, and this is a trick that may come up again on the test. So Christopher, you learned something very important, didn't you? Because if this had been the test, you might have made that mistake. But now you're not going to make that mistake, are you? Well, let's hope not. So A is the radius of Earth plus the height of the shuttle, okay, which is 6,400 kilometers. Ooh, I'm getting a little creative here. Let's get out Big Buddy. Okay, 6,400 kilometers. I'm kind of going slow here, but I don't think that's a bad thing. Plus 400 kilometers, and that's 6,800 kilometers. I should probably do something to this, right? What do I need to do here?
Turn it into MKS.
Yeah, so in this case, it being a length, what do we want?
6.8 times 10 to the 6 meters.
Okay, so Austin's now familiar enough with this where he can kind of do it quickly in his head, and that's fine. If you're not as fast as Austin, and I'm okay with that, Austin. You put kilometers on the bottom and meters on top. That's how we do dimensional analysis. You look up in your notebook. By the way, on the test, there'll be an equation sheet where you have conversions like this. You want to make sure you put the 1,000 next to the meters, put the 1 next to the kilometer. If we put this into scientific notation, 1, 2, 3, 4, 5, 6 decimal places. So our A will be exactly what Austin said, 6.8 times 10 to the 6 meters. And I just got that 6 by counting 1, 2, 3, 4, 5, 6. Why don't we deal with this up here? The mass of Earth and the mass of the ISS is also called the total mass, right? And we'll just analyze the total mass together down here. The total mass is mass of Earth plus the mass of the ISS, which is 6 times 10 to the 24 kilograms plus 400,000 kilograms. Oh, sorry, kilograms. Why don't you guys go ahead and add those up on your calculators?
Professor, what's the symbol for the Earth? Is it the circle with a plus in it?
Yeah, I don't know why I didn't do that. Sometimes I usually that's the symbol that people usually use for the Earth.
All right, I'm just trying to make sure I'm learning that stuff.
Yeah, yeah. I try to get in the habit of doing that's kind of cooler that way too. Anyways, sometimes if I get lazy, I'll just write M sub E if I worry that people might get confused. So I could have done that up here too. It's good to stay consistent. Why don't you guys take your calculators and add those up for me, okay? Oops. Donovan, what do you get? Caroline, what do you get?
It didn't change anything for me. It just kept 6 and 24.
But that's just the mass of Earth. Weren't you supposed to add the mass of the ISS?
Yeah, but
It's negligible.
Oh, okay. Sorry, I was trying to trick you, Donovan. Right? Yeah. This is a 6 followed by 24 zeros. So that's like adding, you know, like $6 billion plus 1 cent, right? It's like, it's hardly even matters. Okay, good. So several of you already remembered that trick. You can actually neglect the mass of the ISS. Or in this case, you could add it, whatever. But it's basically just approximately the mass of Earth, okay? Which is 6 times 10 to the 24 kilograms. All right, so that means I think we're ready. We're gonna write this down, and remember, to get rid of the square, we're gonna put a square root on this side, okay? So P is going to equal, I like using graph paper because I can hand draw a nice clean division bar here. And I'm going to make a nice big neat square root. Okay, so up on the top, I'm going to have 4 times pi squared. I like to, just for the units, open parentheses, 6.8 times 10 to the 6 meters cubed. Oops, sorry, my phone froze. Divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times the mass of Earth, 6 times 10 to the 24 kilograms. Okay, now we find out if you guys can handle this. I think you should try to do it at first without my help. See if you can get the right answer without my help. And then I'll punch you guys through it if necessary. So while you guys are punching, I think I'll just kick back and sip some iced tea. Here's to you. So, you know, tell me what you guys are getting. Tye, let me check you out. Tye, something went wrong there. I think what you did, Tye, is you need to divide right here. Right here, you need to hit divide, and I think you hit times. Is that what happened? Okay, Caroline, show me. Stacy, I don't like. Caroline's got it. Tiffany, sorry, buddy. Arunsak, no good. So far, only Caroline has it. Let's see. Emily, sorry, no dice. Your number is weirdly. Emily, I think you forgot to cube your. There are lots of different mistakes. One of the reasons we're doing this, did you forget to cube, Emily? Yep. Try it again. One of the reasons we're doing this as a lab is because it's so easy to screw this up. And I've discovered extra training here. Blair, that's good, but too many sig figs. Blair, you got it. Donovan, what's going on, homie? Donovan, talk to me. Are you having trouble? Chris, that's good. You got it. Emily, you got it. What are you saying, Donovan?
A little bit, yeah.
Okay. Are you having trouble just punching the whole thing in, or?
Yeah.
Okay. Well, several of you are getting it. Christopher, did you get it? Yes, Christopher, you got it. Okay, so some of you are getting it, not everyone. Yeah, we can. Do you mean, Cameron, can we do this together? Can you want to watch me do it? Now that you've taken your stab at it, let's check out mine, okay? Yes, okay. Let me move my window here. Okay, so I'm going to try to go, can I go vertical here? I'd like to do it so that we can see the, can I pull that off? No. I was just trying to see if I could get the calculator. Oh, okay, there we go. That kind of works. Okay, so I'm going to do this times that squared times this cubed. I don't need parentheses, okay? So 4 times, hit EXP for pi, and then square it. Okay. Now I'm going to times it by 6.8 million, 6.8 exp6. And remember that your cube is right here. So I have to hit shift first, and then I cube the 6.8 million. Now I'll do divided by big G, so divided by 7 exp negative key 11. The trick next is to hit divide here. So I'm going to divide by 6 exp 24. And now I hit equals first. And now I'm going to square root everything because I don't want to forget that. Shift square root. Is anyone still having trouble? Donovan, show it to me. Show me your moves. I want to see your calculator. Okay, something went wrong. Where'd you go astray, Donovan? You not sure?
I don't know.
Oh. Can we try it one more time then? Did I go too fast for you? It's okay, bud. We can do this. You just got to work at it, okay? That's why we're having a training lab here, okay? So don't freak out. Just punch with me. Try it again. 4 times pi. Now we go to square. So far, so good? Do you have that on your calculator? All right. Times 6.8 exp6 okay. Now we're going to cube up here by doing shift and then cube. Do you see that? Is that what you have in your calculator? Okay, now do divide by 7 exp negative key 11. Now divide by 6 exp 24. Now hit equals. Do you see that on your calculator? Now shift and square root. Shift, square root. Talk to me, buddy.
Yeah, I got it, but I have literally no idea what I did wrong last time.
Well, the trick is, Donovan, that there's a million different things you can do wrong. And the only way to learn how to do it right is to do all the wrong things and then start doing it the right way. And then you've done it so many different ways, there's no other way to do it except the right way. So that's what we're doing, okay, buddy? We're training. We're in training right now.
I have a question.
Yeah, sure.
Wait.
Question?
Yeah, sorry, my sister was yelling. Why did we divide instead of multiply?
Okay, sure. I'd like to address that question. The simplest way I could explain it is by going over here to Algebra Alley and telling you, what if I had to do this math problem, which is 6 divided by 3 times 2, right? Now, most people know what that is supposed to be, right? 3 times 2 is 6, right?
Yes.
So you'd expect that to be 1, correct? Now, watch. Suppose I just typed it in that way. Who am I talking to, by the way?
Tiffany.
So Tiffany, suppose I just typed what you see there, 6 times 3 times 2. So if I do 6 divided by 3 times 2, I get the wrong answer. I get 4.
Yeah.
Now that's not good, but what happened here? Let me show you what happened. You typed into your calculator 6 divided by 3, and the calculator evaluates that right away as 2. And then when you type into your calculator times 2, it's doing 2 times 2 is 4. In other words, Tiffany, even though we wanted to do 3 times 2, The calculator thought that we wanted the 2 to be up in the numerator. It didn't realize the 2 was supposed to be in the denominator. If instead, when we get to this point, we hit divide, that will solve our problems. 6 divided by 3 divided by 2. And then you get 1. So does that sort of answer your question?
Yeah.
If you hit times here, the calculator thinks you want the mass of Earth to be on top. Instead, we hit divide to remind the calculator, hey, buddy, this number is also on the bottom. Because your calculator doesn't have eyeballs. It can't tell what's on top and what's on bottom, right?
Okay, yeah, thank you.
You're convinced now, right?
Yeah, I am. I was just really confused. That's why I was getting it wrong.
That's fine. This is a big sticking point. So Tiffany, from now on, we're going to have a rule, you and me and everybody else I'm talking to out there. Anytime something is in the denominator of a fraction, you will always hit divide, okay?
Okay.
Always. All right, cool. A lot of problems actually stem from that. So what should we round our answer to, guys?
$5,000.
Let's do 2 sig figs.
Right. So 5,400.
Yeah. And the units? What are the units?
Meters per second cubed.
No. The cube is distributed to the meters here. So these meters cubed.
Second squared?
Careful. Kilograms,
kilogram.
cancel with kilograms.
Seconds.
That turns
Seconds.
into, yeah, it's the square root of 1 over seconds squared, right? So 1 over seconds squared becomes the square root of seconds squared in our final units, which makes sense because the period is a time, right? We want to have units of time coming out. How long is 5,400 seconds? How long is that in minutes? Donovan.
90 minutes.
Yeah, how'd you get that, Christopher?
Oh, I just used a calculator.
Okay, so let's do dimension. Let's use dimensional analysis, right? Division bar. What units go on bottom?
60.
Did you say a number? We don't do that.
Minute. Seconds, I think, yeah.
And on the top?
Minutes.
Now you can give me your conversion factor.
Okay, on bottom is 60 and on top is 1.
And if you plug that into your calculator, you get exactly what Christopher said, roughly 90 minutes. To answer your question, Austin, yeah, this probably will be the whole problem. Although I did have another one in mind, but I don't know if we'll have time for it. But I'm not done telling you a story yet, Austin. Hey, Austin, does that mean I can see the ISS every 90 minutes? Yes or no?
No.
Why not? Good, why
I
not?
don't know, but I could tell by the way you were saying it.
Can anyone think about why you can't actually see it every 90 minutes?
It like travels over like different parts of the planet, you know, like
Right,
like
but
our
Christopher,
position, you know,
don't
like
forget,
our local field of view it's not always in that field of view.
right, but wait, you're missing a much more obvious point though. Like here's my little crappy globe here. What's the period of Earth's rotation, Christopher?
24 hours.
Right, which is way longer than 90 minutes, right? So try to think about it like, okay, here, I need to put my phone, how do I want to do this? Yeah, no. Okay, I guess I'll just point it down here. So this, I need a little knick-knack or a doodad. Here, this USB thing, this is my satellite, right? And Earth is spinning slowly. I don't have enough, I need to be an octopus. I don't have enough hands for this. So the Earth is spinning kind of slowly, but the ISS is going over it quite rapidly, right? So if the Earth didn't spin, you could see it every 90 minutes, but you kind of have to wait for the ISS to kind of rotate. I'm sorry, you have to wait for the Earth to rotate underneath the ISS, right, Christopher? Like, in 90 minutes, the Earth spins such a small fraction that you might pass over the Arabian Peninsula, and the next time you might pass over Chad in Africa or something like that. Sorry, I know there's kind of a lag on my phone and it's not easy to watch. Let me show you a couple of other cool things instead, okay? Let me stop the share here for just a moment. And to answer the question that Austin asked at the beginning of our lab, one of the simple ways you can do it is to just get yourself a cool app on your phone, like most astronomy apps like Night Sky 2. They will let you know when the ISS is passing overhead. You can also use these websites. One of them is called, like if you just type is where is the ISS, it'll show you like NASA's live tracking station showing you what part of the Earth the ISS is over. You can even like, oh look, we could have looked this up here. It'll show you whereabouts it is right now. Like currently the ISS, according to this tracker, let's go full screen. This is run by the European Space Agency. It's currently traveling over South America, right? Oh, I'm sorry. This is its current location. The yellow arrow shows you where it's coming from after its last orbit, and the white arrow shows you where its next orbit will be. So it's currently over the Atlantic Ocean, and it's going to be traveling up over Spain and Europe. It's going to come down over China and Australia, and it will come back around through South America. So the ISS is on a polar orbit, and you can track when it will come overhead. The short answer to the question is usually it'll appear in your sky once every 3 or 4 days. You'll get a chance to see it. It has to come overhead at nighttime, otherwise you can't see it. And it has to be high enough up in your sky where it reflects some sunlight from the solar panels. I want to show you guys one other really cool thing. On the International Space Station, there's an observation window known as the cupola. And I want to show you guys what the cupola looks like, just to kind of get your imaginations going and to get you guys to think about what it would be like if you could spend time up in this thing. So let's look up the cupola.
You can see it in maps, right? Google Maps.
Oh, the ISS?
Yeah.
I was not aware about that, but that's kind of cool. Let me show you some pictures of the cupola. So the cupola is this observation window. If you have some downtime when you're up there in the International Space Station, you can actually just sit up there and just try to imagine how beautiful this would be if you could just spend time in zero gravity or microgravity, just looking out the window and watching Earth rotate underneath you below. It would be a totally fantastic thing. Here's one of the astronauts doing some cool photography. All right, so he's inside the cupola with a large telephoto lens. And I want to show you guys a YouTube page that I really love. It's called Orbit, A Journey in Real Time. And they have it in 4K. So if you have like a high definition television, you can just kind of put this on in the background. There's a bunch of different ones. Let me show you the one that I really like. Let me try this again here. Okay. This is the one that I like. I like all of them actually. So I put them up on my projector screen sometimes if I'm just like making a tomato sandwich. Sometimes I'll just put this up in the background and it's so beautiful. You're just watching the Earth kind of spin underneath you. It's kind of a fun game to try to guess which continent or which landform you're over. This looks like it might be the Nile here, right? Is that the Red Sea? I think we're somewhere in the Middle East. Maybe this is the Mediterranean. Look at that stuff. You know what's really cool is the nighttime scenes are amazing because during the nighttime scenes, you kind of travel over these cities and you can see humanity like some kind of a weird techno virus inhabiting the surfaces of these continents, right? And you can see where the humans are because there are these rivers of light and electricity that are stretching across the desert. It's kind of wild to look at. So, I mean, this is an hour and a half long because it's a full orbit, right? So we're not going to watch the whole thing, but I'm just telling you about it. So at some point, it's so beautiful. Just put it on if you have one of those fancy high definition televisions or even a good computer screen. Just put this on in the background while you're doing your homework or while you're doing something. You'll find it very relaxing and meditating. Okay, cool. So yes, it does move fast, right? Because think about it, Austin. You're going around the entire Earth in 90 minutes. You can't even get to Florida in 90 minutes on an airplane, right? So this thing is, and guess what's making it move fast? The gravity of Earth. Because p squared is proportional to a cubed, each height above the planet dictates how fast you'll move around the planet. Okay, so that was just kind of a goofy little lab where we got some math training and we learned about the International Space Station. How's everyone feeling? Yes, Emily, you're cool to go. Okay, does everyone have that sheet and you'll just turn that sheet in, right? You've got this thing? Anyone need to see it again or are we good? All right, we're good. Guys, take care of yourselves. I'll render that video and I'll see you guys on Wednesday for homework number 4. Okay, bye.